Hi, so in this video we are going to talk about the linearization of saturation growth model, that where your data has a relationship that looks like y is equal to a x over b plus x, where x and y are your variables and a and b are parameters. So in order to solve this, what we can do is we can convert it to comparable to our standard equation for a line, which is going to be y is equal to intercept plus slope times the x variable. So how would you do that? You can do that if you look at this equation. If you invert this equation, inverting this equation gives you 1 by y is equal to b plus x over ax, or this can also be written as 1 by y is equal to b over a times 1 by x plus 1 by a. And if you compare it to this, your y has turned into 1 by y, your a naught has turned into 1 by a, and your a1 has turned into b over a, and your x has turned into 1 by x. So that's how it is right now. So what you can do is you can use this information and again create your tables. You will have the values for x's and y's. You can write down 1 by x, you can write down 1 by y, and then you can find all the subsequent columns, and you can do summation of 1 by x's, summation of 1 by y, so on and so forth, and then you can put them in the equation for a naught and a1, and that's how you can find all the values that we did, right? So what I'm going to do here is I'm going to solve this problem, which looks very similar to that model, except there is a little bit trick here. So if I look at this function here, which is k is equal to k max c square over cs plus c square, and if I invert this, what I'm getting is 1 by k is equal to cs over k max times 1 by c square, plus I'm getting 1 by k max. Now if you compare this to these variables here, my y is 1 by k, my a naught is 1 by k max, and my a1 is cs by k max, and my x is 1 by x is c squared. And I will use this information to kind of solve for these variables, right, by inputting these to the system and getting output for these two values, and plug them back into this to get our model, which can predict the data correctly, right? So I will switch to MATLAB now. Okay, now for the MATLAB, if we look at the data, we had the C, which was equal to 0.5, 0.8, 1.5, 2.5, and 4. And then we had K values, which is going to be equal to 1.1, 2.5, 5.3, 7.6, and 8.9. So those are your k values. Now if you look at the model, your y is 1 over k, but your x is 1 over c squared. So what I'm going to do is I'm just going to say c squared is equal to c squared, and that is going to be my squared values of the c. And now I can use a polyfit function to fit my 1 by k's and, or I should say 1 by c squared and 1 by k to the first degree polynomial. What do I get? I get 0.202 and I will get 0.90. Now you know from here that this is in the decreasing power. So this is the multiple of the highest power, and this is the multiple of the second highest power. So if you look at this equation right here, the multiple of the highest power was cs over k max, and the second one was 1 over k max. So I can say safely that my k max is going to be 1 over 8 2, right? And what is going to be my cs? My cs is going to be my predicted value there, whatever my k max was, and this cs value is basically just cs divided by k max. So this is k max is already divided, it's taken as 1 by that. So what I'm going to do is I'm just going to use this information to find out the cs, which is going to be equal to a1 times k max, and that will be my cs that I need. So now I need some values for the xp to be put into the equation, so that will be comparable to c squared. So what I'm going to do is my original c values were between the range 0.5 to 4, but remember when I squared those values, I should actually pull up that vector. The value ranges from 0.25 to 16. So what I'm going to do is I'm going to have my x predicted squared to be linspace between 0 to, let's say, 16 itself, or 20 maybe, 20, and I want some 100 values between those, right? And what is going to be my y predicted or my k predicted, so to say, for in the context of this problem? So I would just call it kp is going to equal to my k max times whatever my xp squared values are, and I should close this parenthesis here, and then I have to divide this whole thing by cs plus c squared, which is going to be xp squared in our case here, right? So if you evaluate that, this is what you're going to get. So now if I try to plot this, let me plot the original values of the c squared, or if we want to compare just the c and x, what I'm going to do is I'm going to say c comma x comma, just make it red dots, and my predicted value is going to be my square root, so SQRT of the XP predicted is squared. So if I need comparable to C squared, XP squared was comparable to that. So I'm going to say square root of XP squared, and then I'm going to plot KP with this, right? So this is my vector KP. And if I plot that, it does not recognize the variable x, and rightly so, because we have called it k. And if you look at the plot, that's how it looks like, where it predicts the value for each one of them really correctly. So you can apply this to any scenario, basically, wherever you have a function that resembles, or the data that resembles the linearization of the saturation growth model, right? Now, how do you know, basically, if it doesn't ask for which model to linearize, or which type of model to linearize it, what you can do is you can basically see the scatter of the original data, and you can get some idea from there what kind of fit it is looking for, or what kind of underlying physical phenomena is there. So there are a bunch of different ways that I will talk about some other time, how to find out which functions or which model can be used to predict which kind of data. So this is one of the methods to linearize it.